Great. Okay. Welcome, everyone. This is our 13th Hackaday session on quantum computing. And also, 4 sessions ago, we started doing more coding. So this is what we're going to do. Also, this class, we will be running some quantum katas using the Q# on the teleportation algorithm. I see quite a few new names joining today. Welcome, and welcome back to people who have been in this class. For your information, all of our classes are recorded, and all the slides and recording will be posted on the Hackaday project. So here's the link. Yeah, if anyone wants to post the link in the chat, feel free to do so. And I can also show that later. Well, the class is usually 30 minutes, and sometimes it lasts a little longer. We spend every Sunday discussing one topic. So the format of this is I usually go through some topic theoretically and then show people the coding exercise. We will do some coding together, and then we have some time after that for Q&A. The documentation that we use is from the Microsoft Q# documentation, and the coding exercises are the quantum katas. So we'll go into that for teleportation this class. Just to show people where we are, we have already discussed the superposition, interference, and entanglement concepts. And we also saw the algorithm aspects and linear algebra math aspects about quantum computing. We use the quantum computing language Q# to do the coding so that we can construct some algorithms that would help us get more intuition. So because last class we talked again about entanglement and we used the super dense coding as an example. This class we're gonna reinforce the understanding with a different algorithm, as I mentioned a couple of times, that's teleportation. But before that, and also because there are newcomers today, here are the 3 most important concepts in the quantum computing when you get started. And there are a lot of confusion in these concepts. So I deliberately did this cartoon today to contrast between what has been said in the media and what has caused a lot of general confusion in the general public. And we should think about a different way to describe these 3 concepts. The first one is superposition, where oftentimes is described as 0 and 1 at the same time. And that's often when people first introduce qubits, they want to make a contrast with classical bits. But then saying it's 0 and 1 at the same time is not really helpful for people's understanding. What really is happening is that a qubit is using superposition, which is a fundamental quantum behavior. And if you write out the mathematics, is nothing but a linear combination of these 2 states, 0 and 1, that your system could be in. And your system can have a certain probability of being in 0 and certain probability of being in 1. These are using the analogy of a coin, because like 0 and 1 at the same time doesn't help with our understanding, but then having an analogy of a spinning coin, having half of the time is probably landing on 0 or half of the time on 1. And these amplitudes are what's used in the description here, and their magnitude squared are the probabilities. The second most often actually they're not even discussed in a lot of introductory articles, that then if you heard or learned physics at some point, you heard about wave function and they say measurement is a collapse, but that was quite old interpretation. What we now have understood is that measurement is resulted from these amplitudes constructively and destructively interfering each other, so that the most probable result comes from constructive interference, and that's what we observe in a measurement. Then the third thing is about entanglement. Qubits wouldn't be useful unless we entangle them, and they can give us really powerful applications like what we'll see today, and also we saw in superdense coding last time. But then entanglement is often misunderstood as this mysterious, Einstein called it spooky interaction at distance when he didn't want to believe quantum mechanics, that often is described as changing one of the qubit, the other one will instantaneously change at infinitely far of a distance. But that's not what happens. What happens is that we set up qubits in entanglement, and we know that their measurement results will be correlated. If we measure one of them, we will know the result of the other, even if they're far away. And we don't even have to measure the other qubit to know what the outcome would be based on your measurement of your qubit. If you have learned physics in school, in academia, maybe more than 10 or even 5 years ago, you may find that by learning quantum computing, some of the old interpretation has to be updated. So let's think out of the box and stop using some of the terms that are no longer the proper description. So let's recap what is, how do we set up entanglement? And in this particularly useful case, which is setting up Bell states, these are a set of 4 states that are putting 2 qubits in entanglement. We use them in almost every algorithm. How do we set this up? Is using just 2 gates that we learned in previous classes, using a Hadamard or H gate or a C0 gate. For people who are just joining, these 2 lines means 2 qubits, and then these boxes are gates that we apply onto the qubit. When we have some controlled or connected gates, we have a line drawn to them. This one is a C0 gate. We did in the last class, so it would be really helpful that you go back, if you haven't seen the last class, go back to that one or go to some previous ones to look at the development towards today's class. So this is what happens when you apply a H gate onto 0 and 1. You will put these 0 and 1 into a superposition. So these are 2 possible outcomes depending on what your starting qubit is. And then when you apply a C0, you would then obtain these Bell states. And by doing so, you are entangling your 2 qubits. So based on that, we can set up a fun algorithm called the teleportation algorithm. What this does is, it sounds really sci-fi. It's like you're teleporting from one place to another. But what this algorithm particularly does is to allow 2 people to share information without actually sending their qubit to so one person doesn't have to send a qubit to another person. So here we have the 2 most used name in quantum mechanics, Alice and Bob. That's our characters. So they would prepare these, too far. They would prepare these qubits into a entangled state. So using the H gate and the C0 as we just saw. They separate themselves. They can go as far away from each other as they want. And then Alice obtains another state, another qubit. We label it as a slash. she wants Bob to know what this A/ is, but she cannot, for some reason, directly send it to him. Then she needs to do some trick to her 2 qubits right now. She has her originally entangled qubit with Bob, and then she has this new one. What she has to do is to entangle her own 2 qubits, and then do measurements on each of her qubit. Based on her measurement, she can then tell Bob using a classical method, like calling him or writing a letter to him, telling Bob, hey, this is what I got. So based on my result, you should do either an X gate or a Z gate or both of them to your qubit. And then when Bob does so, according to this table, he would obtain that qubit that is exactly the same as A dash. So this is teleportation. That's by preparing entangled qubits and then separate them and then doing further entanglements, transferring some classical information to allow Bob to reproduce what Alice has in her hand. So let's do this step by step, and we can look at the math step by step as well as coding at the same time. So let's all go to this quantum katas. This is, you can search quantum katas or go to this link here. I've already put it up on the right-hand side on my screen. If this is too small for you, you can zoom in by doing Ctrl+, and I will also do this here on my screen. What we need to do is to find the teleportation kata over here. This is a set of exercises for learning purpose, and we're using the quantum computer language Q# to write out these algorithms. We can go to this Jupyter Notebook option, which then opens up this exercise book on Binder online, so there's no download. This is an installation-free experience, but there are also options where you can download the whole GitHub repo and run it locally. If you want to learn how to do that, go to the Microsoft documentation page. That will help you go through the setup. So now what you need to first do is to run the package for this particular kata. And then let's just look at them step by step. Let's set up the circuit, set up the algorithm. So the first step is asking us to do the entanglement between Alice and Bob's qubits. We were told that they are initially put in the 0 state. And we're also told that this is the Bell state that we want to put this system in. So if we're using this as our target Bell state, we just need to do this table exactly. So if you look at the target Bell state is actually the first one, and your 2 qubits, Alice and Bob's qubits, are already in 0, then you just have to do this circuit. So you apply the H gate to Alice's qubit, and then do a C0 for using Alice's as the control and Bob's qubit as the target. If your state starts with any of the other ones, then you will get different Bell states out. And if that's you would first, usually when we start a program, all of the states are initialized to 0. So if you're asked to do this one instead, you first need to flip the second bit to a 1 using an X gate, which we also learned in previous classes. So now this is your setup, which is successful. And then asking to send the message now. But before that, you have to do a couple of preparations. So Alice's qubit, she has one that's already entangled there, but now she gets another qubit called the Q message. So that's our A dash here. What happens immediately when you first prepare Alice and Bob's bell states, and then you will get this. And this is nothing but rewriting your system into this format. So a 3-qubit system. You have 000, 011, 100, 111 options. And then it's asking you to, the circuit would know we need to set it up as a C0 and H later for Alice's 2 qubits. So you first, you should do C0. This time you're using the message as your control. And then the next step is to apply the H gate to everything, to this Q message after the C0. So let's see what happens. So when you apply the C0, if your control is 0, nothing happens. If your control is 1, the target flips. So that's why now here you have 000 is still 000, 011 is still 011, but 100 becomes 110, and 101 becomes 111 becomes 101, right? Makes sense? Now, after you apply the H gate to Alice's new, so in here the order is, this is your first qubit. So all of them is entangled states in superposition. So on here you're just setting that up. But then, oops, my capital letter was on. Okay, so now you need to return the measurement results of your 2 qubits now. So following this, you can see if, when you're doing a measurement to the first qubit, if it is 0, then what you will get is these 2 terms out of these 4 terms, because it's impossible to have qubit being 1 in this case if your measurement is 0. So these 2 terms gets canceled out. That's what you get when you do a measurement on the first qubit if it is 0. And if you do measurement to your second qubit and turns out it is 0, this term will no longer be there. So we know then this is the term that's left over. And then look at what happens as the third qubit is this one here. And that's exactly what we started as A dash. And that's exactly what what Q message is. So knowing that this table we can set up, if we entangle the 2 qubits in this bell state, we know this truth table can be drawn. And then we know what to do to Bob's qubit in order to get them. So in this case, it's very easy. Both first qubits are 0, and nothing needs to be done to Bob's. But if your measurement of the second qubit is 1, then this term would be the one that's contributing. And this one will be gone. And again, you have a plus here, but now you have alpha 1 plus beta 0, which is a flip of this one, and it is a flip of cube message. So what you have to do is then applying X gate in order to flip it back to this term. That's when your measurement is 0, 1. And if your measurement is 1, 0 or 1, 1, it will follow these two outcomes. So we here just need to set up this circuit. So your measurement results will be returned as classical circuits, and measurement in Q# is just M, which is intuitive. So classical bits is either 1 or 0. In Boolean, it is true and false. So you then just tell it to return to be 1, which then is truth. So this is how you set up so far this part of the circuits. Then the last bit is applying gate to Bob's qubit based on whatever outcome this step gives. So Bob would need to apply gates based on classical information that he gets. So in here, they are Boolean, labeled as bit 1 and bit 2. And this is very similar from what we learned last time in superdense coding. You're setting up a if function. You have this table to represent. If your first qubit is 1, then from this table you see, you have to apply a Z gate. Either case, if your first bit is 1. So you do a Z to QBob. And then if your second bit is 1, you see here, if your second bit is 1, you need to apply X gate, which are these two options. There it is. Will be how you set up. Something's wrong. Did I spell it wrong again? Oh, wrong bracket. Okay, then I will leave the this and the next few setups for you to finish. But I wanted to point out something interesting later. So this is exactly, so you basically constructed the whole teleportation circuit using just 3 steps here. 1, 2, 3. And as seen here from math, you can exactly derive your results, and you see that this is why the algorithm works. So later on, there are some very interesting variations of what we just did. Like, if you start with a different entangled pair, say this was the first exercise, and this was kind of probably the easiest choice, which is very first option of the Bell state, but you have all the other 3 options you can use. So you can have this one as your qubit, as your entangled qubits, or this Bell state or these Bell states. Then correspondingly, this table has to change. So this will be a very good exercise for you to go through this exact same method, but then derive these mathematical outcomes yourself. And it's actually very, very simple. It's nothing but having this minus sign in different places in these terms. And based on that, you have to adjust this table. But then the teleportation still works. You still can transmit information through sending, without sending the qubit, having Bob reproduce your qubit. Three 3.1 is actually also very interesting. It's a variation. And let's see if I want to do this with you or just let you do it. Yeah, okay, I can just show you this here. So 3.1 is saying that we will do the teleportation algorithm, but we don't have to do measurement. This is a measurement-free teleport. So this step here, the if part of the algorithm already is telling you something that perhaps we don't have to do any classical readout. We don't have to do any measurement using the if function. But what about something that's strictly within itself quantum? And we learned about CNOT, which is controlled NOT gate, but we can use the control all kinds of other gates. So here we can repeat the step for the quantum steps like before. So we entangle the Q message and Q Alice like before. Alice, oh, Q message. Doing these if functions here, like construct message step. We could say if my message is a certain value, I can apply the Z gate to Bob's qubit. So we can do controlled because you see that the Q message is giving you the result of the first bit. So instead of having this classical construction, we can just say, use the message as our control bit for Bob's bit. We do a control Z. Similarly, the second bit is giving us the result of the second qubit is giving us the result of the second bit. So we can say that if Alice's outcome is such and such, we would change Bob's. And the such and such is telling us we would need to apply the X. So again, when your first bit is 1, you do Z. When your second bit is 1, you do X. So instead of having some classical part here, you can equally use a controlled method. And I probably typed something wrong here. And is it control Z message? Does not match expected. Got an argument of type qubit. I did this earlier and it was all right. Maybe I will leave this for the audience and figure out why this would be the case. And I can take a look at the message here if there's anyone spotted the mistakes I made here.
Kitty, I think the first argument should be an array, not a single qubit.
The first argument. Oh, wait. I think I might have. Yeah, I think that's what you said, Sina. We can look up the, yeah, okay. Also, we can go to Microsoft documentation. By the way, this is the documentation site for Quantum Development Kit. Everything about Microsoft Quantum that is public. You can find all kinds of gates in the API references. So let's see. Intrinsic. There's a controlled I think for the interest of time, we can look at this together later because I do have a couple more things to show. And I will leave these for people to finish. And then I will also recommend highly task 4, which is the 3 entangled qubits. So you don't have to, you can entangle multiple qubits. And also I talk about entanglements in previous classes. I don't remember which one, but it was quite a few classes before. And you don't have to limit your number of qubits. You can entangle multiple qubits. And I actually have a slide here. We can entangle qubits to make Bell states, and we can entangle 3 qubits, and these are called the GHZ states based on 3 people's names. And when you have n qubits, you can have them also entangled. But then people may ask, then are these the only options for entanglement, for multi-qubit entanglement? No, these are special cases, and these are maximally entangled qubits. So this exercise here actually helps you see there are other options of entanglement, and it helps you construct a state that is not a GHZ, but GHZ is a special case for 3 qubits. So I will highly recommend task 4, for your understanding and entertainment. And I will also point people to this, that when you complete any of the kata, so that's usually how we do this. You work on some of the tasks, but then leave some out for people to finish. You can pick any of the kata and finish them and post them on Twitter or LinkedIn at these. So I know that you have finished it, post a screenshot or photo, and you can get a certificate of printable vector graphic, you can print on anything. So there are people who have already completed, but I've seen some of the later topics. People complete the basic gates, but these are very interesting ones later that you should try. And another word about entanglement, and this was raised last class as well, that entanglement, we can use them like we showed in these algorithms that could be useful, but they can also be very disadvantageous. They can be harmful because you can entangle once you don't have a good control of your system, that you can basically entangle with your environment. And that also includes your measurement systems, where your measurement probe, say, is at the atomic scale, also quantum mechanical. And they can come in when you do the measurement. If you don't control it nicely, carefully, it could mess up your readout, your whole system, because your qubits can entangle with the measurement probe too. So there is a lot of nuances in hardware development and error correction that had to take into account these decoherence. The last thing I want to show is these quantum development workshop. So we have this Azure Quantum that we launched, and this is currently under private preview. Azure Quantum is our cloud service that Microsoft produced to allow anyone to run your Q-sharp algorithm at your desktop or laptop, but then access actual hardware through the Azure cloud. And we are running a workshop to teach how to do that, and also what are the resources for you to develop further and learn. I'll be giving a short introduction talk, and also my colleagues are talking there. You'll be able to meet a lot of the quantum professionals in the company, and as well as meeting other quantum developers. So definitely sign up. That is happening on July 16th. And questions, we can look at questions right away. But then you can also post on the Hackaday project. And if you find the answer to this one in the documentation, also pointed there. The recording is shared on Hackaday as well as YouTube. Just an announcement, next weekend we are not going to do any class. It's a long weekend. It's July 4th on Saturday. It's not particularly relevant to a lot of people here who dialing not from US, but I just haven't had a holiday for many, many months. So I would like to have a long weekend for myself. So let's take a break next weekend. And also for people who just joined the class, they can catch up. Great. Let's take a look at the chat here. Maybe people already figure out. Jimmy asks, can we make the Jupyter notebook? Oh, okay, sorry. Yeah, I already mentioned that. Barry asks, can you elaborate on the principle of deferred measurement? Let's look at that. So, yeah, I'm not entirely aligned with the naming here. Deferred measurement. Well, I guess we're not doing measurement right away, and it's not showing the right image right now. The exercise 3 is called the deferred measurement, and we did not do any measurement. We did the control X and Z. So it's basically saying that we don't have to do measurement right away, or we don't have to do measurement because we know that this table is true. Because mathematically we derive it, and that's how we can set up this algorithm with confidence. Then this here, we don't even have to carry out the measurement. We can just control the Bob's qubit based on the A dash and A here. So we do not do any measurement, but we know what gates needs to be done on. So if we knew what the qubits are, then we can just use them as controls. So I think technically you still have, just practically, you still have to know what they are and do measurements. But this is kind of just letting you see and deliberately letting you use this control gates to see that theoretically it is possible. Yeah, Nathan, thank you for posting the links. Let's see. Android developer. Don't see their name here. Sorry, just shows up as Android developer. But they asked, where is the link for the previous classes? Yeah, thank you for posting that, Nathan. If you go to the website, you will find the slides as well as the links. So this is the Hackaday site. In the file section, these are indeed the slides. And here are the links to the recording, and they don't let you do direct link from there. But if you do view all files, that brings you to this page where you can click on the links. Yeah, sorry about the several steps there. What is the developer conference URL? Yes, Nathan posted that too, thanks. Sumit says Barry essentially means whether a qubit is measured before, after, or during an operation. It will have no effect in circuit's final result. Yeah, thank you. Great. Let's see if there's no other question, we'll finish the class now. 30 minutes is pretty fast. And yeah, I hope everyone gets something out of it. I think another interesting point we can talk about next class is the no cloning theorem. So why can't we just directly make a copy and have Alice copy a qubit and then give it to Bob directly? Why do you have to set like a teleportation or super dense coding type of algorithm? So there is a theorem called no cloning theorem, and mathematically that's quite easy to prove that it's actually not possible to copy a qubit. So we can take a look at it next class. And I think after these entanglement algorithms, we can do some of the other algorithms that are more advanced, like Groover's algorithm, Shor's algorithm, that are very interesting. We have in previous classes also discussed the theory of those algorithms. So Groover, I had a class on that, but we didn't do coding. So it might be interesting to do some coding together. And Deutsch's algorithm and Deutsch-Hose algorithm are very simple. And we have these theoretical classes. And I think, yeah, we should go to Groover's directly. And that's one of the algorithms that's really useful and is using the clever trick of entanglement and interference at the same time. What we have seen with coding so far is just entanglement, but when you involve the interference, will make more complex algorithms more useful. Thank you. No copy code. Yeah, I don't quite get the question Android developer says, but there's no, you cannot theoretically copy a qubit for no cloning theory. Yeah, okay, thanks everyone. That's it.